computer. Okay, you guys have to approve this, I think, for it to happen, but hopefully you'll approve. So we're going to be looking at this sheet here, right? Sheet 8. Yeah?
Yeah.
Yeah.
Yeah. And there are questions around that's the solutions. Whoops. About circuits and the input and output voltages, basically. Okay. So this is really, I guess, around how you would think about making filters, right? Because you want to have some kind of input signal, and then you want to maybe control what your output signal is based on your input. So you might want to pass high frequencies rather than low frequencies, et cetera, et cetera. Does that kind of make sense?
Yeah.
Yeah.
Okay, so that's why we're doing this. And I think this sheet, from what I remember, it's kind of got the same problem, just different permutations on the same problem. All right, but it generally involves something to do with a potential divider and working out the gain and that kind of thing. So I think the most useful thing that we can do is probably go over one example in depth, and then you guys can use the other examples to apply the same techniques, right?
Yeah.
Happy with that approach?
Yeah. Yeah.
So um, I'm going, I'm going to share my document camera, and hopefully you can see this. It's a little bit blurry, but we'll try and focus. Is that okay?
Yeah.
So we're going to do tutorial analog. We're doing analog week 8. Okay. And the first problem that we're asked to, have you got this, both of you got this in front of you?
Yeah.
We've got an input voltage and output voltage system, and I'm going to draw it like this because I find this a nicer way of kind of visualizing it. So what we've got is we've got a 10 kilo ohm resistor, and then we've got some kind of junction, and then the 10 kilo ohm resistor goes to a capacitor, which in this case is 470 picofarads. Do you know what pico is?
Yeah. 10 to the power of minus 12.
10 to the minus 12, good. And then that's joined to a resistor that is 1 kilo ohm. And then that's all joined to the ground. Okay. And what we're told is we've got some kind of input voltage, and I'm going to draw the input voltage. I like to do it like this, and I'm not saying you should do it like this, but I find it a useful way of thinking about it. So that's my input voltage between these terminals, okay? And then the output voltage is between these terminals here. Okay, they're both relative to the ground here, right? Are you guys happy with that idea?
Yeah.
Yeah.
Okay, so what we're going to say is, given that we put in some voltage, what voltage do we get out? That's the thing that we're interested in doing. That's essentially what the frequency response is. Okay. So, well, actually, you guys tell me, what is the frequency response? Because this will have been defined in your lectures, right?
Um, I'm not entirely sure.
It's basically the ratio of the output voltage to the input voltage. Yeah.
Yeah, I think
is
we've
the
done that
frequency
before.
response. Okay, the frequency response H. It's a function of I times omega, where omega is 2 pi times the frequency of the signal. Yeah.
Yeah,
So essentially what we're really saying is that we've got some input voltage A that's e to the j omega t times some amplitude. Okay, it's just a sinusoidally varying voltage. Happy with that,
yeah,
Zia?
Yeah.
Okay, this is how we depict that. So what we're saying is that as we change the frequency, the amplitude of the voltage, the input voltage isn't changing, but the frequency is changing. We want to know how the output voltage changes depending on this frequency. All right?
yeah,
So to do that problem, we're going to think about this in terms of thinking of this like a potential divider. So we could think of this as being the impedance of a resistor, right? And we could think of this thing here as being the total impedance of a capacitor and a resistor in series, couldn't we? Yeah.
Yeah.
yeah,
So we know by our potential divider equation that the ratio of the output voltage Vx to the input voltage Va is going to be this impedance divided by the sum of those two impedances. Okay, happy with that?
yeah,
That's our frequency response function. Now you might be thinking, why is it a function of the frequency omega? Well, we'll see why that is the case in a moment. So sorry about that. Sorry about the switching around. Let's draw a little box around this. So let's think about the complex impedance of the capacitor in series with the resistor. It's going to be 100 kilo ohms, right? Plus the impedance of the capacitor. What's the impedance of a capacitor, guys? You remember this?
It is the value for the capacity. Oh, is 1 over j omega c.
J omega c. Sorry, I should be using J,
Yeah.
not I. Sorry about that. Okay, J omega c. Yeah, thank you. So the total impedance of these two things in series is just 1 kilo ohm plus 1 over j omega c. All right. Now, I'm going to do what is common in a lot of these things. I'm just going to forget about the units for the time being. So I'm just going to call that 1000 plus 1 over j omega c. Okay. Happy with that?
Yeah.
yeah,
And so we're going to put this, we know that the ZR, which is the impedance of this thing here, is just 10 kilo ohms. So I'm just going to write that as 10,000. So let's put those things in. We've got our frequency response. So that's just the ratio of the output voltage to the input voltage. J omega is ZT, which was 1000, sorry, 10,000 over, well, sorry, that wasn't right. Whoops.
zt plus 1 over j omega c.
Let's do that again. The frequency response is ZT, which was this thing here, 1000 plus 1 over j omega c over ZT, which is the thing that we've just written down, 1000 plus 1 over j omega c plus ZR, which is plus 10,000. Okay. So let's simplify that a little bit. We've got 1000 plus 1 over j omega c over 110,000. So 11,000 rather, plus 1 over j omega c. All right, that's our frequency response.
Sorry, where did you get the 11,000 from?
It's 10,000 plus 1,000.
Oh, okay, yeah.
Okay. Now, um, we can simplify this a little bit, he said optimistically. I'm going to multiply the top and the bottom by j omega c. Okay, so then I've got 1 plus 10,000 j omega c over 1 plus 11,000 j omega c. Okay. And then we remember that the capacitance is, what's the capacitance? Do you remember? Either of you? What was the capacitance in the circuit?
470 picofarads.
Yeah, for 470 picofarads.
Okay. So the top of this thing here, 1000 times c is just going to be 470 times 10 to the minus 9, which is 4.7 times 10 to the 7. Okay. So we've got hj omega is 1 plus 4.7 times 10 to the minus 7 times j omega. And on the bottom, we've got 11,000 times this thing, which is going to be 1 plus 5.17 times 10 to the minus 7 as well. So the minus 6 j omega. Is that right?
Yeah, I think.
Gamaliel?
Yeah, probably.
Probably. You got neither of you got a calculator with you?
Yeah, I
Let's put
do.
it back.
All right, Zia, you can check it for me.
Yeah, okay. 11,000 times. Yeah, I think it's right.
Yep.
Yeah.
Now we're going to use a trick here that Dave likes to use. And we'll talk about why we do this trick in a minute. So instead of writing j omega times 4.7, we're going to do j omega divided by the quotient of 4.17 times 10 to the minus 7. So this thing here we can write as j omega. 4.7 times 10 to the 7 times j omega is the same as j omega divided by 1 over 4.7 times 10 to the minus 7. Agreed?
Yeah.
Yeah.
So we take the reciprocal of that thing and we get something like 4.26 times 10 to the 1, 2, 3, 4, 5, 6 over 1 plus j omega over 1.93 times 10 to the 5. 1, 2, 3, 4, 5. Is that what you guys got? No? Zia?
I'm a bit confused actually. How do you get 4.26 times 10 to the power of 6?
So what I'm saying is that multiplying by 5.7 times 10 to the 7 minus 7 is the same as dividing by 4.26 times 10 to the 6. Is that right? You've got a calculator.
Okay, so
So this number times this is the same as this divided by that.
you're saying 1 over 4.7 times 10 to the power of minus 7 equals to 4.26 times 10 to the power of 6?
I think so.
I think that's wrong, to be honest.
Okay, that's fine. You've got a calculator there.
Yeah.
You tell me what you think it is.
So 1 over 4.7 times 10 to the power of minus 7 is 2.13 times 10 to the power of 6.
That does actually make more sense given the numbers. Yep. And how about the one on the bottom?
Okay, so 1 over.
So we think that one's wrong.
That's no, that actually is true. Is 1.93 times 10 to the power of 5.
Okay, so we've got our frequency response function. Okay, both happy with that?
Yeah.
Yeah.
Okay, what are we asked to do next in this problem? Hence determine the break frequencies of the poles and zeros in the response. All right. The break frequencies. What are those? Let's talk about this. So what's a pole? The pole is when the denominator is 0, right?
Yeah. No, yeah. 0 is the numerator.
And the 0 is
The numerator.
numerator is 0. Okay. Now, this bit is might seem a little bit strange, but we're going to temporarily forget about the complex part here. Okay, the J part. We're just going to absorb the J part into whatever our complex frequency is. So For the numerator to be 0, we need 1 plus j omega over 213 times 10 to the 6 equals 0. Agree with that?
Yeah.
Yeah.
And we can see that that occurs when j omega equals minus 2.13 times 10 to the 6. Agreed?
Yeah.
Happy with that, Zia?
Yeah.
So that's why we've done that funny thing about writing the quotient there. It makes this calculation much easier. All right. Now, so let's think about that for a moment. So mod j omega then is just 213 times 10 to the 6. Okay. And if we want to convert to hertz, we're going to say that we're going to take that over 2 pi to give us the frequency in hertz. Yeah.
Yeah.
So that's 2.13 times 10 to the 6. This is radians per second. Okay. So divide by 2 pi to give us per seconds or hertz. 2.13 divided by 2 pi is, Zia?
3.39 times 10 to the power of 5.
3.39 times 10 to the 5 hertz. Yeah, so we could write that as 339 kilohertz if we wanted, couldn't we?
Yeah.
So that's the break frequency for the 0. Both agree with that?
What exactly is the break frequency again?
It's the frequency at which the 0 occurs.
Oh, okay.
Yeah.
Yeah.
And so now let's think about the pole. The pole then, that's when the denominator is 0, right? So we need 1 plus j omega over 1.93 times 10 to the 5. That's got to be equal to 0. So we need that j omega equals minus 193 times 10 to the 5. And the magnitude of that then is 1.93 times 10 to the 5 radians per second. Okay?
Yeah.
As before, we have to convert to frequency in hertz. So we take the radians per second and we divide by 2 pi. And Z is going to give us what that is.
1.5 divided by 2 pi. 3.07 times 10 to the power 4. 3.1, let's say.
So we could call that 31 kilohertz. Yeah, roughly.
Yeah.
Yeah.
Or 30.7 kilohertz. Yeah. So that's the pole. So the frequency of the pole is this, and the frequency for the 0 is this. Okay. Right, that's the first part of the problem. Now it says describe the effect of zeros and poles on the amplitude response of a network at, below, and above the break frequency of the 0 or pole.
Is this not the part when we use the body approximation?
Yeah, what did you call it? The Bode approximation?
Yeah.
What is the Bode approximation?
It basically gives you approximation about the values of when the poles and zeros happen, and then it's almost like a good approximation. I don't know how to describe it.
Let's think about the different things. Okay, so we know that at the zero, the frequency response is going to be zero, isn't it?
Yeah.
Let me just have a little bit of a think about this. Right, let's enumerate. Let's go through the different possibilities. Okay, one by one. So let's think about the frequency response here. So for j omega much bigger than the zero, okay, far above the zero. Yeah.
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 We can look at this equation here and we can say, well, if j omega is much bigger than this thing here, then the numerator is basically j omega, right? Over that. If j omega is much bigger than this, then this term is much bigger than this term, right? And we just get left with
Yeah.
j omega over 2.13 times 10 to the 6 divided by, if j omega is much bigger than this, then it's also much bigger than that. So we're just going to get left with j omega over 193 times 10 to the 5. Yeah.
Yeah.
Those bits are going to cancel out. So we're going to get left with 193 times 10 to the 5 divided by 213 times 10 to the 6.
It's almost 11.04.
11.04.
Yeah. Oh. Is it 1.93 times 10 to the power of 5 divided by 2.13 times 10 to the power of 6? Or
Yes,
is
it
it
is.
all?
Yeah.
Oh, okay.
Yeah.
Sorry. So that's okay. That's 5.
Oh, hang on a minute. We need to compute the gain. We're not interested in the frequency response. We're interested in the gain, first of all. Right. What's the gain? Oh, God. Right. What is the gain?
Mm.
Right. Somebody tell me what the definition of the gain is for the circuit.
The V out minus V in.
It's 20 log 10 base 10 and output voltage over input voltage.
Zia reckons this. Okay. Do you agree with that, Gamaliel?
I'm not sure.
Well, I don't know. Have you been going to the lectures?
Yeah.
Zia, where did you get that number from? Where did you get that
That's what
equation from?
that's okay. So that's what the so basically the gain is 10 log to the power of output power divided by input power, and since power equals v squared over r, so it's like 2 times 10, which is going to be 20 log 10 to the power of v out over va.
That's right. So let's go through that argument then. So Gamaliel, the gain then is actually the log, the gain in bells, right? Which means taking the log to base 10, I guess, is the output power divided by the input power. Yeah? Px divided by Pa. Happy with that?
Yeah.
Well, the ratio of the output power to the input power is the same as the square of the ratio of the output voltage to the input voltage. Okay?
Yeah.
And just to avoid any problems, we'll do the magnitude of the square, okay?
Yeah.
The square modulus, because it's complex, so we'll square the modulus, okay? So we're going to call that then the log to base 10 of Vx squared over Va squared. Okay? That's the log to base 10 of the magnitude of x divided by the magnitude of Va, all squared. So by our rules for logs, that's 2 log to base 10 Vx over Va. Okay?
Yeah.
So that's the expression for the gain. Now, you might be thinking, where's that in bells? Okay, so in decibels, then the gain is 10 times that. Okay, to convert to decibels. Does that make sense, Gamaliel?
Yeah.
Zia, does that make sense?
Yeah.
So that's our gain. All right. Now I'm going to write it like this because it's going to be a bit easier. So I'm going to put the power of 2 back inside. So I'm going to have 10 log to base 10 modulus of Vx squared over modulus of Va squared. Okay. That's 10 times the log of the magnitude of the frequency response squared. Okay.
Yeah.
Happy with that both?
Yeah.
Yeah.
Now, that's our gain in decibels. Now, why am I writing it like this? The reason I'm writing it like this is, let's think about our frequency response. Okay. Remember, it looked like this: 1 plus j omega over 2.13 times 10 to the 6 over 1 plus j omega over 1.93 times 10 to the 5. So the magnitude, sorry, I need to put j's, don't I? The magnitude of that is Well, the square of the magnitude of that is the square of the magnitude of the top over the square of the magnitude of the bottom. Yeah?
Yeah.
Yeah.
Okay. Now remember, for complex numbers, the square of the modulus is the sum of the square of the real part plus the square of the imaginary part. Yeah?
Yeah.
Yeah.
So that thing there is going to be 1 plus omega squared over 2.13 times 10 to the 6 squared over 1 plus omega squared over 1.93 times 10 to the 5 all squared. Happy with that?
Yeah.
Yeah.
So this is what's going to go into our gain. Okay. And because we've taken the moduli here, we don't need to worry about the complex part. So the gain then is 10 log to base 10. I think, I hope this is all going to work, of this stuff in here. 1 plus omega squared over 2.13 times 10 to the 6 squared over 1 plus omega squared over 1.93 times 10 to the 5 squared. Okay,
Yeah.
that's the gain, if I've done it correctly. Right, now let's think about what each part of this is doing. I mean, guys, I'm slightly freestyling here. So remember that if we've got the log of A over B, it's log A minus log B, isn't it? Yeah?
Yeah.
So we can write the gain then as 10 lots of log to base 10, 1 plus omega squared over 2.13 times 10 to the 6. So that's all squared. Yeah?
Yeah.
Minus 10 lots of log to base 10, 1 plus omega over 1.93 times 10 to the 5, all squared. Happy with that?
Yeah.
Yeah.
So this first bit is the contribution from the zeros, and the second bit is the contribution, sorry, from the zeros, and this is the contribution from the poles. Yeah?
Yeah.
Happy with that?
Yeah. Yeah.
I think that's my interpretation of this. So um so let's go through these one by one. So let's think about the zeros to begin with. if omega is much less than the zero, okay, then this part here is almost zero, isn't it, compared to one? It's much smaller than one.
Yeah.
So the whole log of that is going to be close to zero. So it's going to have negligible effect. Happy with that?
Yeah.
Yeah.
Okay. Now let's think about if we're much larger than this zero frequency. Then if we're much larger than this zero frequency, the first term here looks like 10 log to base 10, 1 plus omega over 2.13 times 10 to the 6 all squared. If omega is much bigger than the denominator, then that's approximately, that thing here is much bigger than 1, right? This term here is going to be much bigger than 1. Agreed?
Yeah.
Gamaliel?
Yeah.
So then that whole thing there is going to be 10 log to base 10 omega over 2.13 times 10 to the 6 all squared. Yeah.
Yeah.
Which is 20 log to base 10 omega over 2.13 times 10 to the 6. Yeah.
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 Which is 20 log 10 omega minus 20 log 10 2.13 times 10 to the 6. So what we can see then is that the frequency, when the frequency is much larger than the zero part of the frequency, it contributes 20 decibels for each increase in omega by a factor of 10. Yeah?
Yeah.
Each time I increase omega by a factor of 10, so if omega is 10, then log 10 of 10 is 1. If omega is 20, sorry, 10 to the 10, then log 10 of 10 to the 10. Sorry, if omega is 100, then log 10 of 10 is 2. So it'd be 20 times 2. So each time we increase omega by an order of magnitude, the gain increases by 20 decibels. Yeah?
Yeah.
Yeah.
So the zeros increase the gain by 20 decibels per decade when omega is much bigger than the break frequency, the zero frequency. Okay. What about at the frequency now? So if omega equals 2.13 times 10 to the 6, then 10 log to base 10 of 1 plus omega over 2.13 times 10 to the 6 is 10 log 10 of, sorry, squared is log 10 of 2, isn't it? If omega equals 2.13 times 10 to the 6, then omega divided by 2.13 times 10 to the 6 is just 1. We square it, we get 1. We add 1, we get 2. So it just gives us 10 log 2. Is that right?
Yeah.
Yeah.
That's the zero contribution. What's 10 lots of log 2, Zia?
It's 3.01.
So it increased. So at the 0 frequency, the 0 contributes 3.01 decibels. Yeah.
Yeah.
Okay. So that's the zeros done. We've done this term here. We've seen what this term contributes. If omega is much less than the 0 frequency, then this term doesn't contribute very much. If it's much greater, then for every decade increase in omega, we find that the gain increases by 20 decibels. And we found that at the frequency, the 0 frequency, the contribution due to this term is 3 decibels. Both happy with that?
Yeah.
Yeah.
Okay, now let's look at the poles. We're going to do the same thing here. So contribution from the poles, let's call that G omega from poles is this thing here, this term here, minus 10 log 10, 1 plus omega over 1.93 times 10 to the 5, all squared. Agreed?
Yeah.
Yeah.
Okay, so let's think about what happens due to the poles. As before, if omega is much less than 1.93 times 10 to the 5, so this term is much less than this term, this thing squared is going to be really, really small, and log space 10 of 1 is just going to give us about 0. So that implies it's negligible. Yeah?
Yeah.
Yeah.
If omega is much greater than 1.93 times 10 to the 5, then G omega from poles is approximately equal to minus 10 log to base 10. So omega is much bigger than this term. So this term dominates over 1, and we just get left with omega over 1.93 times 10 to the 5 squared. Yeah?
Yeah.
Agree, Gamaliel?
Yeah.
That's minus 10 log to base 10 omega squared plus 10 log to base 10, 1.93 times 10 to the 5 squared, which is minus 10, minus 20 log to base 10 for omega plus 10 log to base 10, 1.93 times 10 to the 5 squared. Happy with that?
Yeah.
Yeah.
Zia?
Yeah.
So what that's saying is that each decade increase in omega decreases the gain by minus 20 decibels. Yeah?
Yeah.
Okay. Right. And the final thing we need to do is at the frequency. So at the break frequency where omega is 1.93 times 10 to the 5, then the contribution to the gain from the poles is minus 10 log to base 10 of 1 plus 1 over 1 all squared, or log 2. Zia's already told us that log 2 times 10 is about 3, so that's about minus 3 decibels.
Yeah.
Yeah? So at the poles, it decreases the gain by 10 decibels. All right, all happy with that?
Yeah.
Yeah.
Okay, now let's sketch out the gain using our equation from earlier. So let's remind ourselves what the gain is. We remember that the gain was 10 lots of log to base 10, 1 plus omega squared over 2.13 times 10 to the 6 squared, all over 1 plus omega squared over 1.93 times 10 to the 5 squared. Yeah.
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 And we know that if omega is much, much less than 1, if it's very, very small, then the gain is going to be about 10 log of 1 plus a small number divided by 1 plus a small number. So the log of 1, it's going to be about 0. Okay?
Yeah.
We know that if omega is much, much bigger than 2.13 times 10 to the 6, then we know that the gain is going to be approximately equal to 10 log to base 10 of this term's going to dominate over this term's going to dominate over this. It's going to be approximately equal to omega squared over 2.13 times 10 to the 6 squared over omega squared over 1.93 times 10 to the 5 squared. Both happy with that?
Yeah.
Yeah.
And what did we find out? We found out that that's the same as 1.93 times 10 to the 5 squared over 2.13 times 10 to the 6 squared, which is what, Zia?
Give me 1 second, please.
It's going to be 20 lots of log to base 10 of 1.93 times 10 to the 5 over 2.13 times 10 to the 6.
Okay.
It's going to be about minus
Minus
20, I think.
minus 20.937, which is minus 21.
About minus 21.
Yeah.
Okay. Um, all right. Okay, so we can think about sketching this out. And we're going to put omega on the bottom axis, and we're going to put the gain on the y-axis, okay? And we said when omega is much, much less than 1, we know that the gain was about 0. So we know we're starting at 0. And we also know that as the frequency becomes much, much bigger than this, the gain tends to this thing here. So when omega is much, much bigger than 2.13 times 10 to the 6, we know that the gain is going to be about minus 20.9. Okay? So we know that we're over here when omega is large, and we know we're over here when omega is small. Happy with that?
Yeah.
Yeah.
The question is, where does it start to change? All right. It's got to get from this point down to this point, right?
Yeah.
Yeah.
Um, let's remind ourselves of what the frequencies were for the pole and the zero. So for the zero, we had omega was 2.13 times 10 to the 6. And for the pole, we had omega is 1.93 times 10 to the 5. Okay? Yeah?
Yeah.
And we know that's roughly where the key things are happening. Remember when we talked about so the key area here is going to be around 10 to the 5, 10 to the 6, 10 to the 4, right?
Yeah.
Yeah, because the zero's around the zero's sort of at this point here. So that's kind of our zero area. And our pole's around this point here, right? So we're going to be up here with a pole. Okay, and that's the zero. Happy with that?
Yeah.
Yeah.
And we know that in between, we know that when we're that's the pole, that's the zero. Okay. Remember from our discussion before, we said that each increase above the pole decreases the hang on, I've lost my notes on this. Um, hang on a second. Let me just find out where we were. So for the poles, we said that if the frequency was much bigger than the pole, then we're decreasing by 20 decibels per decade. Okay. So we've got to be decreasing by 20 decibels per decade. So we're going to be doing something like that. The gradient there is going to be like minus 20 per interval. All right.
Yeah.
So when we're going from 10 to the 4 to 10 to the 5, or here, actually here, that's almost 1 decade, isn't it?
Yeah.
Yeah. 2.13 times 10 to the 6 compared with 1.93 times 10 to the 5. You can think of that as 2 times 10 to the 6 and 2 times 10 to the 5. Agreed, Gamaliel?
Yeah.
They're almost different by 1 decade, and we've said it's got to decrease by 20 decibels, which is decreasing by 20 decibels. So it's basically got to do something like this. Okay.
Yeah. Which is very close to body approximation.
This is our Bode approximation. Okay, we're just basically joining a straight line. If we wanted to, we could evaluate what the gain would be at 10 to the 5. Okay, if omega was 10 to the 5, let's have a look at what the gain is. We can use our gain formula. So this was our gain formula. All right. So we can put 10 to the 5 into this thing, and we'll have, let's see if we can just zip and do both of those things at the same time. 10 log to base 10 of 1 plus 10 to the 5 over 2.13 times 10 to the 6 squared over 1 plus 10 to the 5 over 1.93 times 10 to the 5 squared. Okay. I think that's going to be roughly, well, that's roughly 10 times log to base 10 of 1 plus 1 over 400, because 10 to the 5 divided by 10 to the 6 is 1 over 10, times 2 is 1 over 20, squared is 1 over 400, over 1 plus 10 to the 5 divided by 1.93 times 10 to the 5 is about 1 over 2 squared. Do you guys agree with that?
Yeah.
Gamaliel?
Yeah.
So 1 plus 1 over 400 is about 1. 1 plus a half squared. So the top's going to be about 1. The bottom's going to be about 1 plus 1 over 4, which is 5 over 4. Yeah? So it's going to be about log to base 10 of 4 over 5 times 10, roughly. Zia, can you tell me what that is?
The 10 log. It's minus 0.969.
Oh, shit.
If I put the actual number in it, that would be minus 1 point something.
Hmm. Um, have I done something wrong there?
Um,
Should we plot it on Desmos and see what happens? What
Yeah.
was that? You all want to plot it on Desmos?
Yeah.
yeah.
Okay, let's have a look on Desmos. Right, hang on. So, right, let's share the screen. You guys see this? Desmos?
Yeah.
Yep.
Um, okay, let's put in our function. So we're going to use the function that we just had, which was 10 log to base 10. How do I put in log to base 10? Hopefully that will work. 1 plus frequency squared over 2.13 times, no, how do I put a multiplication symbol in? Times 10 to the 6. We've got to square all of that. Okay, that's the contribution from the zero. Okay, you can't really see it because it's too small, but let's see if we can change the axes to logarithmic axes. Um, okay.
Yeah.
I'm struggling because it's quite hard to use Zoom at the same time as doing this because I can't see the axes. But so this is the contribution from the zero. Yep.
Yeah.
Now let's put
Yeah.
on the contribution from the pole. So it was minus 10 log to base 10. I assume I'm doing log to base 10 correctly in decimal.
Yeah. That's right, I think.
1 plus the frequency divided by 1.93 times 10 to the 6.
5.
Thank you, Zia. All squared. Okay. What's happened? Where's it gone?
Mm.
Am I doing is this thing wrong I've written here? I just do log, is that better? Ah,
Can you change one of the x's to, I don't know, y or some other letter? Probably that might fix.
if I delete that, get this. I put that in. I don't understand this. I'm going to try using my own graphing thing, okay? Let's try it on Grapher. Okay, can you guys see this?
Yeah.
Yeah.
Right, so let's try this again. So we're doing 10 lots of log 1 plus x over 2.13 times 10 to the 6 all squared. And I need to so it's so hard doing anything on Zoom because anytime I try to move anything, I get these weird Zoom options. Hang on, axes, format axes. Ah, right. There we go. So my claim was that this is the the gain part, right? The pole part.
Yeah.
I feel like I might be just doing something really stupid. Have you guys had a go at doing this?
Um,
No.
no, not really.
Do you still see this?
Yeah, I think that should work out. See.
Should be the same, right?
Yeah,
Oh, it's probably possibly because I've got both axes as logarithmic. Hang on. I want log linear, don't I?
yeah, there you go.
Ah,
There we are.
Yeah,
That's what I did wrong. I want log linear. Okay. So yeah, so you were right, Gamaliel. Sorry, Zia. When we put 10 to the 5 in, we get about -1.
yeah,
Yeah. Okay, so that's what we've just sketched out on the using the Bode
yeah,
approximation. Okay, so I'm going to stop the share now. And okay, so that's basically what we've just sketched out.
yeah,
All right, happy with that, guys?
yeah,
yeah.
So there is a solution in the notes with the Bode approximations a little bit gives a little bit off at 10 to the 5, okay? But you know, that's basically the Bode approximation is the approximation for what we've just sketched using the graphing package. Okay?
yeah.
Yeah.
Right, does that make a bit more sense, guys?
It
Yeah.
does.
I hope so. Um, and it's a little bit tricky, but you just work through systematically through each thing, okay? When you've got your guess, you can estimate the gain based on different frequencies by thinking about where you are on different points of this curve. Okay, so using our guess here, using our guess, we'd say that the gain at 10 to the 5 would be about -10 decibels, but that's slightly off. Okay, but it's not miles off because it's in decibels.
Yeah,
Um, okay, right. So I'm going to stop the FaceTime thing. I'm going to go back to Face. So that's how I've been approaching these problems. And I think you just go through it systematically. You need your definitions for what gain are. You need your definitions for what the frequency response is. And then it's a case of being systematic. I don't think it's too bad. The other problem on this sheet is essentially the same kind of problem, but you're given a different kind of circuit. So you have a different kind of potential divider. And I think you have to um, add impedances in parallel as well as in series. Okay. But
yeah,
I'll leave you guys to do that at your leisure. All right.
Yeah.
yeah,
Okay. So thank you then, chaps. I will see you on Thursday and we will do whatever the next sheet is then.
yeah.
Okay.
Thank you very much,
Right.
John.
Cheerio,
Yeah.
guys.
Thank you.
See you.